And what I'm going to look at is I'm going to look at a massive projectile. In other words, in this case, M1 is much, much bigger than M2. So here, what we're doing here is that you have a bowling ball is shot at a stationary golf ball. So what am I seeing here? Well, physically, I should be looking at what? Well, I imagine that I have this large mass, right? This is my bowling ball. And of course, this is my object one. So as it's coming in with some initial momentum. Now I have my tiny blue ball here. And when I'm thinking about my blue ball, I'm thinking about it like this here. And what you're seeing here is that it's looking like this guy right here. And this guy is 2 here. And this guy is what? It's at rest. And so what do we expect physically to happen here? Right? So physically, what should we be seeing? What we should be expecting to see here is that if a bowling ball hits a stationary golf ball, you have to admit that most of the momentum has to stay with the bowling ball. So I would think that it's sort of like, right, a fly. I mean, it's just not going to affect the motion of it that much. So when I look at this guy, I would expect that the momentum of one to be initially the momentum of the final scenario here. And then afterwards, what would you expect the golf ball to be looking like? Well, afterwards, you'd probably expect that this guy, would you think that it's going to have a lot of momentum or a little momentum? What would be your guess? So my question is, what do you expect for this momentum? Well, if I draw a bar diagram, it's got to look something like this here, right? So the first thing I'm going to do here is that I could imagine that I have this amount of momentum coming in. And of course, it's got to be coming in like this. And when I look at the momentum of the golf ball, we already know that it's 0. So when I'm looking at my bar diagram here, what I'm seeing here is that I would think that the momentum of the bowling ball is not going to change that much. Right? Because it has such a huge mass and it's moving, so I would expect that. So if I look at the momentum of the golf ball, it's getting a little tiny sliver of this thing. A very, very, very tiny amount right here. Very, very, very tiny. So what I'm seeing here is that most of the momentum stays with the bowling ball. And very little goes to the golf ball. Right? That's a little bit surprising. And the reason why that might seem surprising here is that if we go and look at the simulation, what am I going to see here? Well, if I go in and I look at the simulation once again, okay, so now I'm going to change the masses. So I'm going to change that one to 2. And I'm going to change this guy to 0.1. Okay, so it's about 20 times bigger. And what I want to do here is that I definitely want it moving in this direction. And I definitely want this speed to be 0 because we want a stationary situation here. Now, what I want you to pay attention to, ooh, that's not what I wanted. Okay, what I want you to pay attention to is look at the speed of the bowling ball coming in, and then look at the speed of the golf ball going out. So here we go. So that's what it is there. And then afterwards, now let's go look at this thing. We didn't measure this length, but what we'll find here is that this length is a little bit shorter than the previous situation. So you could see that this is roughly, that's half, it's about 0.7 to 0.8 in length. But look at the shock of the ball number 2. It's moving very, 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 very fast. So let's go analyze this thing, right? So if I reset this thing, and if I do the collision, oops, I thought I reset it. Oh, wow. Of course it's going to go that way because it has to start. I had to have changed this direction to do that, but I won't do that right now. So let me go back to my OneNote so that we can go and look at this thing. So what I'm seeing here is that you may have been surprised that there's a lot of speed, right? There's a lot of speed, but not very much momentum. So then I look at the elastic collision equations, and what do they tell me here? So if I go and I raise this up, I'm going to see that I have V1F is then going to be M1 minus M2, M1 plus M2 plus V naught initial. And then, of course, I have my 2. So then, in this case, all I'm doing here is that 1 is much, much bigger than M2. And so now I can approximate these guys. And the way I'm going to approximate them is that if M1 is much, much bigger than M2, I can ignore M2. So this should be approximately something like this, which tells you that the speed of the golf ball, the speed of the bowling ball coming in is roughly what it is going out. They're approximately the same. That's not a surprise. But look what happens in this other scenario here. I'm going to get M1. I'm going to set this to 0. I can't do that with the numerator. And so then if I do that, you see that this is coming in at twice the velocity. So now we can see here that we have 2 conditions that we're looking at, right? And that 2 is, the question is that, why is it twice? Okay, so if I go and I ask a question, how can the golf ball which not wide, but which has a tiny mass move twice as fast after the collision. And well, one way that we can do here is that it's a frame of reference picture here. So let's imagine what happens here. So now what I want you to do here is that let's look at reference point. So when we see the big billiard ball coming in, or the big bowling ball coming in, right? It's coming in with this initial speed. What we're seeing here is that when I observe this collision here, we know that this speed here initially is 0. So when we're watching this thing from this reference point, we're saying, right, here's our observer, we're seeing that this ball is going to be moving twice as fast. That's what the calculation says. But that's hard to see why it's twice unless you do this type of thing. So now what we want to do is we want to change our reference. So we're going to change reference frame. Okay, we're going to change reference frame. So now what we're going to do here is that we imagine that our observer is going to be where? It's going to be standing on top of ball number 1. So if our observer is right here, according to him, the ball is at rest, right? If you're in a car, you're moving at 75 miles an hour. Well, according to you, you're not moving at 75 miles an hour. It's the rest of the world that's coming at you at 75 miles an hour. So what you're seeing here is that the observer is at rest with ball 1. So now look what happens here. So according to him, the ball is coming in at what? It's coming in with some initial speed like this. Oh, I called that 1. I should call that 2. And what you're seeing here is that probably to give a good sense of what is going on, we're going to pick this to be the negative direction and that to be the positive direction. So before the ball comes in, it's coming in the negative direction, right? So this is before. And then afterwards, what you're seeing here is that the ball is moving in what direction? Well, it's moving in the opposite direction. There's a collision. So if you look at this guy here, the ball is approximately moving with what it initially had, but of course in the opposite direction here. Okay, so we got to be careful here. I'm going to erase that because I need to put that minus. So, my direction is a little bit slippery here. So this is the opposite direction of the initial velocity. And it's that minus sign that's really important. So when I look at this guy here, what you're seeing here is that what we're really asking for right here is, what is the change in velocity of the golf ball? Well, what you'll find here is that it does this. So the change in velocity is going to be, let's see, to try to make it a little bit more clear, how about if I call this VA and this guy VB afterwards? And so when you're looking at this, we could see that the final velocity should be VB minus the initial velocity. But then check this out. Look at VB. VB is in the positive direction. So then this should be roughly V2 initial in the positive direction minus, but then V2 initial is in the negative direction. So I get minus V2 initial like that, which then says that this is roughly twice the initial speed that you're supposed to get. So that's a really important fact, that by looking at the frame of reference change, we could see why it's twice the velocity. So let's talk about summary here now. So in the first case, we looked at mass equals to this. And what we find here is that there's an exchange of momentums and kinetic energies. Right? There's a straight up exchange. So if I look at this guy, I see that I have this amount of momentum coming in. And then afterwards, I get 0 momentum. And if I look at what happens here, I start off with 0 momentum, and then afterwards, I get that amount of momentum. So in this scenario here, what you're seeing here is that you're seeing the following thing, that you are literally exchanging momentums and kinetic energies. So if I look at the kinetic energy in this case, check this out. The kinetic energy of 1 should be, now note that this is going to be different because it's V squared. I'm going to draw them a different height. So if I look at this kinetic energy, it looks like this. This is the kinetic energy initially of 1. And then afterwards, all of that kinetic energy gets transferred to what? To this final kinetic energy. Even though it initially starts at 0, and then this guy afterwards, we see here, has a kinetic energy of 0. So you're seeing the exchange of kinetic energies and momentum. Let's look at the next case. In this case, we had a very heavy bowling ball. So what actually happens in this case here? So here's where it becomes quite subtle. What you're finding here is that in this exchange, you get maximum momentum transfer. And what we saw here is that when we have this object that's coming in, let's say it's this big right here, we see here is that we almost recover all of the momentum. So if I look at this scenario here, so now when I look at, I could see that this guy is 0, but then afterwards we saw that this had big momentum transfer. Most of the momentum went right towards where? It went in that direction to the right. So the bowling ball gets maximum momentum transfer. So it turns out that when you have maximum momentum transfer, you have small kinetic energy transfer. And to sort of like set this apart here, let me go to 3 here. In 3, what we're seeing here is that we have just the opposite situation. Oh, I need to go down a little bit. And what you're finding here is that in this exchange, you have minimal momentum transfer. And this one makes sense because look what happens here. I look at what's coming in with the target. And let's say that I have this amount of momentum. Afterwards, we saw that most of the momentum stayed with the bowling ball. So if I now look at my total momentum situation, what we're seeing here is that this momentum, again, is a 0, and then this is the transferred momentum. And we could see here that this is just some little tiny bit right there. And that's what I mean by maximal and minimal transfer. But in this case here, it turns out that you have less energy transfer. And what I mean by energy, of course, is kinetic energy. And in this case, we see that the golf ball's going twice as fast. And why is there less here? Because the bowling ball is moving very slowly. Whereas in this case, you have more energy transfer. And what do I mean by that? Because now the golf ball is moving about twice as fast. So therefore, because it's moving twice as fast, then that means that you're transferring more. And so that's really what actually, you got to look at these 3 cases. So with this in mind, we want to then go